And welcome to 19-2, where we're going to be talking about the hydrogen ions and acidity. In this whole unit, we're going to be introducing to you basically the idea of concentration of hydrogen ions, what acidity and basicity is, and then we're also going to introduce you guys to the pH scale and what's called the pOH scale. So, first things first, as you learned in 19-1, water can act as both an acid or a base, and because of that, it can react with itself. Where, let me go ahead and get my pen back and ready to go here. It can react with itself, where the water molecule, in one case, one molecule will donate a hydrogen, the other molecule will accept the hydrogen. Because the first hydrogen doing the donating, we would consider that an acid. I guess I could do that in red just to stay consistent with what we've been doing. This would be the acid. And the other water molecule, because it's doing the accepting, would be behaving as the base. Alright? What would form then, because water, the second water, the water on the right, is behaving as an acid, its conjugate pair would be the hydroxide ion, because that's what's left when the water donates that hydrogen ion. The water molecule on the left, because it's accepting a hydrogen, will form hydronium. That will become its conjugate acid. And so these two would be a conjugate pair, and these two would be a conjugate pair. This whole process is called autoionization or self-ionization, because water is forming ions from itself. These water molecules on the left are neutral. The two units on the right are ions, and water caused itself to do that. Now, typically we don't write it this way. We write it the second way that you see right here, where we just say that water splits into hydrogen and hydroxides. Typically we don't write hydronium as a molecule. When you write the hydrogen ion like so in water, in an aqueous solution, it's assumed to be hydronium. There are virtually no free protons floating around. All right? If it is, it's incredibly small for a very, very brief moment in time. Now, this autoionization only happens to a very small extent, and in fact, at equilibrium, the hydrogen concentration and the hydroxide are only going to be 1 × 10⁻⁷ molar. Now remember, that really means 0.12345 like so. Very, very small. Alright, but it does happen. And it is in an equilibrium, and the equilibrium position will be the same, or the equilibrium constant will be the same at a given temperature. So therefore, if we rewrite the equilibrium, let me scroll back up just a little bit so we can see the reaction. The equilibrium that we're looking at is water in equilibrium with the hydrogen ions and the hydroxide ions. And so therefore you can write this as an expression: K equals the products raised to their coefficients power, of course those are both 1s, divided by the reactant raised to its coefficient power, but you leave it off because you're dealing with water in the liquid form. And so this is the equilibrium expression. Now we give it a special name, just like we did with we had KEQ or KC in when you're dealing with the equilibrium constant in general. We actually call this KW because it's the equilibrium that water exhibits, and we call it the ion product constant because KW is the product of two ions that form water. So that's why we just call it the ion product constant, or people just will call it KW. And so now if you plug in the concentrations at equilibrium, which are 1 × 10⁻⁷, this will equal 1.0 × 10⁻⁷. This will be 1.0 × 10⁻⁷. And when you multiply those two together, you get 1.0 × 10⁻14. So therefore, if we rewrite this as a full expression, KW will always equal the hydrogen times the hydroxide concentrations, and at 25 degrees Celsius they will always equal 1.0 × 10⁻14. The reason why water is considered a neutral compound or a neutral solution is because these two quantities are actually equal to one another in just standard water. However, that's not always the case. If you add a compound that changes the concentrations where the hydrogen is greater than the hydroxide, remember, hydrogen is the acidic ion, hydroxide is the basic ion. That comes from the Arrhenius definition. If the acidic ion is greater than the basic ion, then the solution will be acidic. On the other hand, if the acidic ion is less than the basic ion, well, then we would say that the solution is basic. But as we mentioned before, if those two quantities are equal, like they are typically in water, then the solution is considered neutral. So that is why water is neutral. It has both acidic ions and basic ions in the solution at the same time, or in the water at the same time. But because they're in the same quantities, we say that the solution is neutral. So let's go ahead and calculate on the next page and determine whether or not various solutions are acidic, basic, or neutral. Okay, let's go ahead and try this first one. You have the hydrogen concentration is 6 times 10 to the negative 10 molar. So if we say that Kw equals the hydrogen times the hydroxide, and that equals 1.0 times 10 to the negative 14. We know that the hydrogen is 6.0 times 10 to the negative 10 molar. We don't know the hydroxide, but the product has to equal 1.0 times 10 to the negative 14. So now if we solve for the hydroxide by dividing both sides by 6.0 times 10 to the negative 10, of course, these terms will divide out. The hydroxide then will equal 1.0 times 10 to the negative 14 divided by 6.0 times 10 to the negative 10. And when you perform that calculation, the hydroxide is 1.67 times 10 to the negative 5 molar. So, if the hydrogen, which is the basic ion, is 10 to the negative 10 to the negative 10. The hydroxide, which is basic, is 10 to the negative 5. This quantity is larger than the acidic quantity, so therefore this solution will be basic because the hydroxides are in greater concentration. All right. Let's try the next one. You have Kw. They give you hydroxide is 3 times 10 to the negative 2. So Kw will equal the hydrogen times the hydroxide, which is 3.0 times 10 to the negative 2, and that's going to equal 1.0 times 10 to the negative 14. If I divide this over to the other side, I'll be left with hydrogen equaling 1.0 times 10 to the negative 14 divided by 3.0 times 10 to the negative 2. And when I perform that calculation, I get 3.3 times 10 to the negative 13 molar. So once again, if you compare the acidic ion, which is now 10 to the negative 13, and you compare that to the basic ion, which is 10 to the negative 2, this one is greater than the acid, so therefore this solution once again is basic. Alright? Go ahead and try Part C and Part D, and in the next podcast we'll go over those and then introduce you to the idea of pH. We'll see you next time.